Okay, so welcome back, everybody. Um, so as I mentioned yesterday, we're on to chapter 3 and on to second order equations. So on to second order equations, which will begin in chapter 3. Now, as I've mentioned previously, our approach to second order equations is going to be a lot different from our approach to first order equations. First order equations, we were able to analyze and solve like entire kind of classes of first order equations. So we didn't have to restrict ourselves to like a specific first order equations. We could talk about, linear, semi-linear, quasi-linear, fully nonlinear. We could talk about each of those things. That's not really going to be how we deal with second order equations. There is, in fact, a classification of second order equations that can be done. And we will talk about that by the end of the course. There is a nice kind of classification of second order equations, and we'll get into that. But it doesn't really necessarily work in the same way as it did for first order equations. So for the rest of this course, we're going to mostly focus our attention on specific equations. And almost all of our attention for the rest of the course is going to be focused on three specific equations. So there's the big three. So the big three second order equations. And also I should go ahead and just say, if you're expecting a kind of approach that you saw in ODE in Math 246, you're not really going to get that here. Where in Math 246 for ODEs, right, if we were talking about linear ODEs discussing, a second order equation versus a third order equation or fifth order linear equation, we could actually discuss those things, at least the general theory for those things, kind of all at once. It didn't really matter, like the order didn't really matter, and if we remember how this worked for linear equations, especially, we'll say just like constant coefficient linear equations, right? Um, so the only thing that happened when you changed the order for an ODE, if you had, say, constant coefficients, was the degree of your characteristic polynomial changed, right? But, if we have tools to be able to find roots of the characteristic polynomial, whatever degree it is, then that really didn't bother us too much, right? The underlying process was exactly the same. That's not going to be how it works for PDE, really. At least that's not what we're going to see at all in this course. So we are going to be focused on three specific equations for the most part for the rest of the course. So these are our big three second order equations. I've already mentioned them. So the wave equation, the heat diffusion equation, and Laplace's equation. As I previously mentioned, if you've taken, say, Math 463 or some other course you've taken, harmonic analysis, of course, you will have seen Laplace's equation before. Now, we are going to begin with the wave equation. So here's where we start. We start here. Why? Because in some key ways, it is most similar, I'll put this in quotes, most similar to first order equations. And we begin with, like, the entire topic of chapter 3 is the wave equation in one spatial dimension. So we understand it first in one spatial dimension, and then we'll talk a little bit more about the wave equation in 2 and 3 spatial dimensions. After that, that'll be in chapter 4. And the good news is for one spatial dimension, we're going to find general solution. We're going to find specific formula for solution with auxiliary conditions. We're going to be very happy. We're going to be able to say a lot of stuff based on that. For the 2 and 3 spatial dimensions, the way that we kind of approach it is we're going to see what sorts of things it would satisfy. We are going to see some specific, like some very particular solutions to the thing. But in terms of actually writing out solutions, that will have to come later after we've done some intermediate stuff that's going to help us with the other two of the big three as well, the heat equation and Laplace's equation. So, so this is most similar to first order equations in the following sense, right? So first of all, what is the wave equation saying? Right? What is the wave equation modeling? How did the wave equation arise? So the wave equation is meant to model a propagation of some kind of disturbance, right, in a medium. So, for instance, right, in this previous, in the first order cases, we had some equations that kind of modeled the same sort of thing. And so the idea is I have some like initial disturbance, right? Say in the one spatial dimension case, an initial disturbance in like a string. String has some physical properties, right? It has some tension, it has some mass density. Okay, string, wire, whatever, and there's some initial disturbance, and I want to model like the propagation of that initial disturbance, right? And that initial disturbance shows up as a wave, so it's the propagation of that wave. Now you might ask yourself, but wait, didn't we already have first order equations that modeled that very thing, right? So recall, right? Recall we had the first order equation that looked like this, right? That had some initial signal or some initial disturbance in this way. This is our transport equation. Well, we already saw that this transport equation, the resulting solution profiles from this thing always worked in the following way, right? If our initial disturbance was this sort of thing, then as t increased, you have this thing moving to the right at some constant speed c. Its overall shape is preserved. That's fine and all, right? But this clearly doesn't model every type of wave or perturbance of, some disturbance of medium, your string. This is not going to model everything, right? All of these sorts of waves we want to talk about don't behave in this manner, so this is not going to be enough. We also saw, I think we used minus x here. In the example we did, we also saw a variable speed, there we go. Okay. Looks ugly, so let me do it again. Okay, something like that, right? So we saw what this looked like. This was a different situation from this. This is not the picture that I got when I plotted these profiles, right? You might remind yourself what this looked like and what the effect of this variable speed was. But it also didn't really model waves, like every single wave I was trying to think of. Also, we had Burger's equation, or the Inviskid-Burger's equation, which formed a very important type of example for us. All right, so something like this with initial condition specified here. Okay. And what was it that Berger's equation was modeling, right? Where now our variable speed is actually the speed is proportional to the solution itself. The idea was that, well, the higher this initial disturbance wave, right, the higher points on the wave move faster than the lower points. And so what you had is maybe if this is your initial disturbance, you got something possibly like this, where eventually this top is moving faster than the bottom, and you get some like wave crashing over thing going on, which was nice. That was exactly what we were looking to model there. But again, this is not going to capture everything that happens with a wave or some disturbance of string, right? How do I know that it's not going to capture everything? Well, physically, if I expect to model a wave or disturbance, like an initial disturbance of my string or my medium, if I expect to model this thing accurately, so I want to involve basically all of physics that I can. Now we'll talk a little bit later about what it means versus like if we're talking about Newtonian versus like relativistic, right? Some other sorts of considerations I might have to throw in, but let's say that I'm focusing on the Newtonian case, right? So if I'm looking at, you know, Newtonian physics, I want to incorporate all of it that I can here, right? What am I going to need? Well, Newton's second law Newton's second law involves what? It involves second order derivatives. Right? It involves second order derivatives. And so it means we expect our wave to be modeled by a second order PDE. Okay. So if we want to talk about an equation that is going to more accurately model like a wide class of these phenomena, well, I would expect the equation that would do that to be a second order one. Okay. Okay. So what is the wave equation in one spatial dimension? So wave equation in 1D. It is u sub tt is c squared u sub xx, where c is some constant. Here's like the classical 1D wave equation. Okay. So we seek a function u of one spatial dimension x, one time dimension t. So if you like, you can always write the wave equation as, you know, it's 1 plus 1 dimensional, but we really only refer to the spatial dimensions, right? The dimensions we can see, that's what we refer to here when we talk about the dimension of the wave equation involved. And here it is, right? This is my wave equation. Now, there's a derivation for this. I'm not going to do the derivation, but I will tell you where it is. So in your e-copy of textbook, the derivation is on pages, I believe, 84 through 87. If you're interested in the actual physical derivation of the wave equation. That's where you can find it. What is this c in this derivation? This c squared is like t over rho, where rho is the mass density, which in, say the simplest case would be taken to be constant, and this T is constant arising from tension of the one-dimensional thing in question. So the idea is we think about this as a string, right? So, okay. Now, here's the thing. What if I want to consider a PDE, right? What if I want to consider PDE plus auxiliary condition to describe fully some situation that involves this equation? What would I need, right? What would I need to hope for a unique solution? So what would I need to hope for a unique solution? Well, I would need the initial displacement of the string. That is telling me something about this initial disturbance, right? So one, I need initial displacement of string. You may have guessed that in this formulation of the wave equation, in this derivation, since I mentioned Newton's second law and things, you may have already figured out what is it that's happening here, right? This U is this is telling me about position, right? This is measuring displacement. Okay, so initial displacement of string, that is an initial value of the solution itself. But this isn't enough to pick out among all of the, if I think about trying to generally solve this, completely generally, this is not enough to pick out a specific solution among that infinite family of solutions that I get from the general solution. And you should know this, you already knew this from physics, but you also already knew this from ODE stuff, right? So in ODE stuff, right, when you had a first order equation, you only needed a single initial condition. But when you had a second order equation, how many conditions did you need? You needed an initial condition on the solution itself, like the unknown function, and you needed an initial condition on the first derivative of the unknown function, right? So let's go back to ODE here. If we had a second order equation, right, what did we need? We needed I should have just written it like this, it's fine. So we needed some initial condition and some initial velocity, right? Some initial condition on the derivative of this thing. We needed both of these things. In fact, whatever the order of your ODE was, you needed the same number of initial conditions, right? So if it's second order, you needed 2. If it's third order, you needed 3. If it was a third order ODE, you would have needed conditions on the unknown function y, its first derivative, and its second derivative, right? So that was what you needed in order to actually pick out a unique solution from the infinite family of the general solution, right? The unconditional differential equation. And so the other thing I need here is the initial velocity. So initial velocity of the string, i.e. its value, this initial value at u sub t, right? So these are the things that I need, right? Now, what solution would I get? I can just kind of think ahead for a second here. What solution am I going to get if I were to choose both of these to be 0? So initial displacement is 0, initial velocity is 0. naturally, what should I expect, right, just from my kind of physical intuition, what should I expect the unique solution to be? Well, I should expect the unique solution to be 0 for all time, right? The displacement of my string in that case should be 0. The string should just be like at equilibrium, right? So that's exactly what I would expect, right? Without some other terms here that are not present, like some kind of external forcing terms or something like that, I would expect this thing to just be 0 forever. It'd be the trivial solution. And that's exactly what I get, and we'll see that specifically. And so the question is, if this U is measuring displacement, then when I say that we're talking about like modeling the propagation of some disturbance through the string, what is it that is propagating here, right? Like what is it that's propagating? Because if we think about measuring some strip of the string, then this string is just like bobbing up and down, right? So like it's bobbing up and down. So its displacement is just like up and down. So any particular given piece of the string is just bobbing up and down some amount. But what do I mean when I say that like this is propagating along the string? So of course, like you can do this yourself. You can take a string and do this very thing and kind of see what it is that's going on. But what is it that's propagating along the string? It's energy. Energy is being transported across the string, right? So the initial disturbance propagates energy along the string. Okay. And the reason why it's important to never, you're not going to divorce like the physical intuition from the math that you're doing here, because the physical intuition is going to help you a lot with kind of understanding why some of these math things that underlie all this stuff actually work. We're going to talk about something called the energy method. It's extremely important and very useful. For instance, that has a very simple and nice physical interpretation as to why you would do that, right? So thinking backwards, maybe you'd be like, well, why would anyone think to do it this way? Why would anyone think to do this trick? And if you're okay with the sorts of answers like, well, because it works, right? And people just tried a bunch of things until they worked. That's certainly one explanation. But the easier thing by far is to use physical intuition here to try to see something that would work before you even try it. A couple things I'll say. First of all, before we move on and talk about this, what is the wave equation in 2 and 3 dimensions? So wave equation in 2D is what this is. U sub t is equal to c squared times u sub xx plus u sub yy. So here we are going to seek a solution u of xyt. The thing being disturbed now is no longer a string. It's no longer a one-dimensional thing. It is a two-dimensional thing. So you can think about this being like a drum, right? The top of a drum. It is some surface, right? So here is some surface, and I can think about an initial disturbance. Maybe you could think about this as some kind of rug that is, you've pulled taut, and then you ruffle it, right? You introduce ripples into the rug, okay? What about in 3D? Well, it's more of this. It's u sub tt is c squared times u sub xx plus u sub yy plus u sub zz. And we seek a u of xyz t. Okay. Now, there are simpler ways of writing this. We write this as c squared times the Laplacian of u, and c squared times the Laplacian of u. I mentioned this on the first day of lectures here for this class, where the Laplacian is the Laplacian with respect to the spatial variables, right? So you can think about the Laplacian being the trace of the Hessian, however you want to think about the Laplacian. Laplacian is this operator, right? It takes u and takes its pure second order x partial, adds it to its pure second order y partial if it's 2 dimensions. If it's 3 dimensions, the Laplacian does the same thing, except now there's 3 variables to do it to, right? Okay, so that's how this works. Okay. And of course, we're going to talk about these. We're going to talk about these, the wave equation in these. So just hold tight, and we will talk about those in a few lectures. Okay. So let's, as I said, since I'm not going to derive this thing, let's go to my general no conditions, just wave equation in 1D. What's the first idea? Well, I kind of have no idea what's really in my toolbox here. I'm not really sure what to do with this, right? We haven't solved a second order equation, so it's completely up in the air as to what I should do here. Let's first of all rewrite this. In fact, you may have seen the wave equation rewritten in this way already before. Maybe this is the way the wave equation, if you've seen it before, has been expressed to you. I could put everything on one side. Okay, so this is u sub tt minus c squared u sub xx is equal to 0. Okay. All right, so what's going on here? Well, what if I massively abuse some notation here, right? And I write this in a factored form. So what do I mean a factored form here? So what I'm going to do is I'm going to first think of what's going on here as an operator on u. Right? What do I mean? So I'm going to rewrite this as like del sub t squared minus c squared. Here, let's before I do that, let's do it like this. So I'm going to write this as del sub t squared of u. That's what I mean by that. Minus c squared del sub x squared u is equal to 0. And what I've done here is I've set up this notation so that del sub t squared of u, it takes an unknown function u and it takes its t partial twice consecutively. Just like del sub x squared u takes unknown function u and it partially differentiates it twice with respect to x. So with that notation defined, yes, this is exactly the same as this. So I think of these objects as taking in a function u and spitting out some other function, so something that I've done to you, right? And this thing that I've done to you, of course, is a differentiation operation. So these are what are referred to as operators, right? So these are operators. An operator you can think of as taking a function, spitting out some other function. If it's a differential operator, it's going to spit out some other function that involves like derivatives of that thing, right? Okay. Now, why did I rewrite this equation like this? So that I can, there's something suggested here. Okay, there's something suggested. First of all, since these are differential operators, and differential operators are linear, what do I mean by linear here? I mean linear in the sense of like a linear transformation is linear, right? So I mean that you can break it up across sums and you can pull constants through it. So maybe as a little aside here, just because it's useful to see this. So it means that if I have a differential operator, say d, applied to constant times function plus another constant times function, it means that this is constant can be pulled out times derivative of function plus second constant can be pulled out times derivative of function. So this operator breaks up across these linear combination objects, right? The operator respects the act of linear combination. Okay, so operator applied to a linear combination is a linear combination of the operators. That's what it means to be linear. So this is linear, so that what that means is that I can pull this u through it, so I can rewrite this as del sub t squared minus c squared del sub x squared times u is equal to 0. Where this thing in parentheses is one single operator. Okay. This one single operator I call box. So I've rewritten this as an equation, call it box u is equal to 0. Right? So what do I mean that this operator is box? So let's just think about what this does. What does this operator box do? It takes u, an unknown function, and differentiates it. It takes its partial derivative twice with respect to t, and subtracts from that c squared times its double x partial, right? Which is exactly what this equation is. Okay, so that's what my operator box is. Now, why would I want to do this? So this is often called the D'Alembert operator. We'll see D'Alembert's name again, I promise. So this is called the D'Alembert operator. And the reason for rewriting this is because now let's pretend that we're way back, right, in middle school or high school, and we're looking at an expression like this. And I have something squared minus something else squared. Well, what is that? Like algebraically, right? That's difference of squares type object. So difference of squares is one of my favorite things to be able to factor, right? I can just immediately factor. So notice that box factors. So now algebraically we're treating these operator objects just like they're x, y's, and z's showing up in some algebraic expression. And so box can be rewritten in factored form as how does this work, right? How does difference of squares work? It's if I have, right, x squared minus y squared, right? That's x minus y, x plus y, right? That's how difference of squares works. So this would be del sub t minus c del sub x times del sub t plus c del sub x. Okay. Now, what does this mean? It means that if I take this equation here, down here, since this thing factors, what do I get? It means that box u, right, my original wave equation, so u sub tt minus c squared u sub xx, that's really box u, which is really the operator del sub t, minus c del sub x applied to del sub t plus c del sub x applied to u. But wait, what have I done here, right? So if this is going to be equal to 0, what have I done here? I have factored this operator in such a way that it's almost like I get two equations. But what are the two equations I get? So it is almost like I get two first order PDEs. What would they look like? So since I've factored them, it looks like the two first order PDEs I get are this operator applied to u is equal to 0, which is like u sub t plus c u sub x equals 0. And the other one I get is like u sub t minus c u sub x is equal to 0. But what are these PDEs? These are both first order transport equations, right? So, of course, at the very beginning of lecture today, this transport equation was exactly what was our original model for this sort of thing. And now it looks like we're getting two of these things. Now, this is not exactly what's going on. This is just some kind of nice intuition, right? But this factoring method leads to insight that allows you to do this. And we're going to prove that all of this kind of works and is justified in this way. But this is just kind of telling us what I can expect the general solution to be. In fact, what is the general solution to this? Right? So what's the general solution to this? This is like g of x minus ct was what we found to be the general solution, where g is the the function, the data function. And the solution to this is like some other function f x plus ct. And so what should my general solution to my original equation box u or my wave equation be? My intuition from this factoring is that it should be a sum of these things. Because this was my general solution to the first order transport equation. This is the general solution to the other first order transport equation, right, where instead of my speed being c, my speed's minus c. Okay. And so this factoring of this operator has led me, my intuition tells me that this thing is like, this is what the general solution to this equation should look like. Right? Okay. So now let's actually state this and prove it. So general solution to the 1D wave equation. So the general solution, that is without reference to any conditions, right? The general solution to u sub tt minus c squared u sub xx is equal to 0 is of the form u of xt is equal to f of x plus ct plus g of x minus ct for arbitrary C2 functions f and g. one variable. Yeah. You can check yourself that if those functions have enough regularity, so if they have two continuous derivatives there, just do the check, verify using this formula and the chain rule to show that they will satisfy the wave equation. Okay. And so that factoring of the operator is a trick that I will be able to do for some very special second order equations in this same sort of way. This kind of gives me the idea for this. To prove this, we can use a change of variables. The change of variables is nice because it's suggested by our factoring. Right, so here was how we factored it. This factoring actually tells us what the change of variables should be to rewrite the PDE. We're going to do that trick of notation that I mentioned on like the first or second day of class when it comes to changing changing the variables in a way and rewriting them as a function of those same variables. So so do change of variables where Cc will be x plus ct and eta will be x minus ct. All right. So here's C, here's eta. All right. So thinking of it this way, right? It's almost as if the wave equation involves a directional derivative with respect to like two different directions, right? Here's one and here's the other. That's kind of what's going on here. So let's apply the chain rule here. So applying the chain rule, what is the partial of u with respect to x? So by chain rule, this should be the partial of u with respect to c times the partial of c with respect to x plus the partial of u with respect to eta times the partial of eta with respect to x. Okay. But the partial of both c and eta with respect to x is just 1. So this is a sum. The u partial with respect to c plus the u partial with respect to eta. And similarly, the partial of u with respect to t, right, is the partial of u with respect to c times the partial of c with respect to t, plus the partial of u with respect to eta times the partial of eta with respect to t. But the partial of c with respect to t is c, so this is c times the u partial with respect to c, plus the partial of eta with respect to t is minus c, so this is like minus c times the partial of u with respect to eta. Okay. So if we write this in operator notation, right, the x partial of u is it's del sub c of u plus del sub eta of u, and the del sub t of u is c del sub c of u minus c del sub eta of u, which I can write as, now if I write it like this, if I try to combine these two equations and put them in terms of my D'Alembert operator, right? So the first thing I want to compute is the first factored part of the D'Alembert operator. So this is del sub t of u we'll say minus c del sub x of u. What is that? All right, this is, so let's see here. Del sub t is, so del sub t of u is this c del sub c of u minus c del sub eta of u minus c times that. So this would be minus c del sub c of u minus c del sub eta of u. These terms cancel, and what I'm left with is minus 2c del sub c of u, or sorry, del sub eta of u. Okay. The other one, similarly, so del sub t of u plus c del sub x of u is what? This is positive 2c del sub c of u. Okay. And so, what do I get when I try to put my wave operator, right, box u, which is, del sub t squared minus c squared del sub x squared of u. If I try to write that in this factored form, so in this factored form, factoring my operators is del sub t minus c del sub x times del sub t plus c del sub x applied to u. According to this, this is like, so that is a multiplication of these two operators. So this is like minus 4c squared del sub eta or c. U is taken to be C2, so it actually doesn't matter what order those things occur in. So I'm just going to write it as del sub c eta of U. And so I have taken my wave equation, changed variables, and now my wave equation, if this is equal to 0, I get a new wave equation where I have some constant here, minus 4c squared. So I can divide through by that and just have a very, very simple equation. Thus, my PDE, my wave equation, transforms from u sub tt minus c squared u sub xx equals 0 to u sub, like, eta c is equal to 0 in the new variables. Okay. But we already know, so we've already seen on, I believe we did this in lecture 1, that this PDE has general solution u of c eta, which is f of c plus g of eta for generic arbitrary functions f and g. Right. But then let's go back to our original variables. This translates to function u of xt is f of, recall, c is x plus ct, eta is x minus ct. So this is f of x plus ct plus g of x minus ct, which is exactly what I wanted to prove. All right, that's it. Okay. So that does it. All right. And we're very happy to have this general solution so readily available to us here, right? So bring this back for a second. My general solution to 1D wave equation is exactly solution of this form where f and g are arbitrary C2 functions. Okay. All right. So a couple of things that can be pointed out here, right? What is what's the dimension of CT, right? If we thought about this C being tied in with our transport equations, right, in the first order case, C was a speed, right? It was a velocity. And of course, T is time. So the units of CT here is velocity times the time, right? Well, velocity is, like distance over time times time. So that should have the dimensions of length, right? Okay. So this has dimensions of length, which is fine because you're adding it to x here or you're subtracting it from x here. So you have dimensions of length plus length, that's good. Length minus length, that's good. So, but if we think about this for a second, right, they have dimensions of length, they denote positions along the string. But what does this mean overall in terms of the solution here? Well, right, f and g are functions of a single variable here. So what is it that's going on in my solution, right, in like the picture? Well, in the picture here, there's an interplay between space and time, right? Right? Like my u, of course, is a function of two variables, x and t, but we see how in the general solution these things get put together, right? So there's like an interplay between space and time here, which when you think about it at first can be a little bit confusing, but actually this is something that is going to like kind of be like a fundamental property of propagation of waves. So you'll get used to it. This is definitely a feature, not a bug here. Okay. All right. So then, of course, the other thing to notice more, the bigger picture here, the solution to my wave equation is a sum of two solutions to two transport equations, right? So one is a transport equation that moves to the right at speed c, and one is a transport equation that moves to the left at speed c, right? So, and of course, each signal keeps its shape as time changes. But of course, the question is, you might guess, right, that if I were to add a condition to this, or if I were to add conditions, say, on the initial displacement and initial velocity, that f and g would just correspond directly, right? One of these would be like the initial displacement function and one would be the initial velocity function. But that's not exactly how this works. Okay, so that might be your first guess, that one of these is like your initial displacement data function and the other is your initial velocity displacement function, but that is not how this actually works. So to actually see the dependence on the data here, we have to talk about the initial value problem and its solution. So the IVP and its explicit solution. So this explicit solution to this IVP is known as D'Alembert's formula. So I told you you'd hear that name again. So D'Alembert's formula is what this is. Okay. So, as was mentioned previously, for this thing to be well posed, what do you need? You need both an initial displacement and an initial velocity condition imposed on your wave equation. So to get a unique solution, you can expect, right, to need exactly this sort of thing. So we have the 1D wave equation, right, IVP for a 1D wave equation. What does that look like? This is u sub tt is equal to c squared u sub xx, right? And I'm looking to solve this for x some real number and for t greater than 0. So after some initial time. And then I have initial data. I have initial displacement given to me by a function phi of x, where x again is real number. So this is ranging over the reals. And u sub t of x0, this initial velocity function, is given to me as c of x. So all these two conditions taken together with the PDE, this forms my IVP for the wave equation. Okay. Now, unless otherwise specified in some, starred exercise or something where we've messed with the regularity of phi and c, you can assume that these are C2. So assume that phi and c are C2 unless otherwise stated. Okay, we know what the general solution, what form it has, right? So the general solution, remind ourselves from the previous page, is u of xt is f of x plus ct plus g of x minus ct, right, for functions f and g. Okay, we've specified initial displacement and initial velocity. The question is what should f and g be? As I said, you might think that like f is phi, for instance, and g is c, right? Maybe that's what you think. So it turns out that that's not exactly the case, but actually it's not too hard to figure out exactly what these things have to be. This was actually originally written down in 1746. So D'Alembert. So D'Alembert's formula. This is from 1746. So D'Alembert's formula is the following. Here's theorem. If u of xt solves, we'll call this asterisk. So if u of xt solves asterisk, right, then the form it has to take in terms of these conditions, u of xt is equal to 1/2 times phi of x plus ct plus phi of x minus ct plus 1/2c times the integral from x minus ct to x plus ct of c of s ds. Okay. Now, first of all, how do I go about showing this? So firstly, now that I've given you the formula, you can check that this actually solves the wave equation. In fact, quick exercise for you. This wasn't assigned on a homework, but you can do this. So exercise, check that this solves asterisk. Really quickly, we can just check the initial conditions, of course. So let's check the initial conditions. If t is equal to 0, I get, if t is equal to 0, then this integral here is the integral from x to x, so that's 0. Here I have 1/2 times phi of x plus phi of x, so 1/2 times 2 phi of x. I get phi of x Oh, okay. So there's my initial displacement. For the initial velocity, I would have to take the t partial here. You need to remember what it means to differentiate with respect to variables showing up in limits of integration here, right? You can do this with a version of the fundamental theorem of calculus if you like. Okay, and this sort of, so you will see that if you do this differentiation and plug in 0, you'll see that that is in fact c, and this thing solves the wave equation. But you should check this on your own. It's good practice working with this thing. I should note that most of what we're going to say for the rest of this chapter is actually a consequence of D'Alembert's formula. So there's a ton of stuff hidden here in this formula, a ton of great info for how wave propagation works. Okay, there's actually like a ridiculous amount of info from this that can be derived just from this this formula. And I mean, of course, this purports to give us a solution to this, like a unique solution to this IVP. So of course, like this is it. Like everything has to be here, right? So basically, everything you want to know about 1D wave equation has to be kind of answerable or showing up somewhere here, one would think. All right, so so this is very important. So let's actually go through a quick argument as for why this works. So let's do proof. So previously, we knew that the general solution has to be of the form u of xt is f of x plus ct plus g of x minus ct. Okay. So really, all we need to do is just try to figure out how f and g are related to our initial conditions, right? So we ultimately want to determine the relationship between f and g and phi and c. That's basically all we're doing here, right? Okay. So then what do I know? If so, I know that u of x of 0, x0 here is f of x plus g of x. So I know that, right? But, so that's just using this general solution. But I know that from the IVP, of course, that's my initial displacement phi. So phi of x has to be a sum of f and g in this way. And of course, if I compute from this formula, if I compute the t partial of u, what should I get here, right? This is going to be, so, well, really I need the t partial of u evaluated at 0, so let's do the t partial of u evaluated at 0 here. So the t partial of u evaluated at 0 is what? This is going to be the derivative f with respect to t here is going to be c times, using the chain rule, this is f prime. Plugging in 0, this is going to be f prime of x. So this is going to be c f prime of x, right, minus, in the same way, the derivative with respect to t, this x minus ct is minus c. So this would be minus c g prime of x. And that is my c. So you get two relations here between phi and c and f and g, right? Okay. Okay. So we're because the computations we're going to do would be kind of confusing if we left this as x, so let's replace x with some variable that doesn't occur anywhere else in these things, so that, because here, right, these two expressions, they only, like x is all that shows up here. I can worry about these things later. So replace x with, say, alpha, right? Just some dummy variable alpha. So rewrite these two expressions. This is like phi of alpha is f of alpha plus g of alpha, and c of alpha is c f prime of alpha minus c g prime of alpha. Okay, so here's my two expressions for phi and c. Well, what if I take the first equation, I differentiate it with respect to alpha? So then phi prime of alpha is f prime of alpha plus g prime of alpha, right? Okay, so now I have two expressions. One is for phi prime, the other is for c. Okay, but now I can actually solve this system for f prime and g prime. So solve, maybe if I rewrite this over here, phi of alpha is c f prime of alpha minus c g prime of alpha. And so I now have a system. I want these two things to be simultaneously true. I want to solve this system for f prime and g prime. So solve for f prime and g prime. Okay, and of course, you know, when I say solve for f prime and g prime, this is going to be in terms of like phi prime and c, right? In terms of phi prime and c. So then solving this, I get f prime of alpha is going to be 1/2 phi prime of alpha plus c of alpha over c, and g prime of alpha is 1/2 phi prime of alpha minus c of alpha over c. So now what do I do? Now I can integrate with respect to alpha for both of these. So integrate. What do I get? This means that f of alpha is 1/2 phi of alpha plus 1 over 2c times the integral from 0 to alpha of c of s ds plus some constant. Right, we'll call it c1. And g of alpha is 1/2 phi of alpha plus or minus 1 over 2c times the integral from 0 to alpha of c of s ds plus some other constant c2, we'll say. So c1 and c2 are arbitrary constants. So how do we determine these? Well, of course, going back to my general solution is a sum of f and g. So I'm going to be adding these two things together. So in the sum of these two things, I actually don't care about C1 and C2 individually. I just care about their sum, right? But since we know that phi of alpha is equal to f of alpha plus g of alpha, this was the first expression I came up with here. That means that when I add these two things, right, c sub 1 plus c sub 2 is actually 0. So it doesn't matter what c sub 1 and c sub 2 are. When I add f and g, which is what I am required to do, right, to find my solution, these things cancel out, and so I don't have to worry about those. Okay. Now, we know that f and g, right, if we want to write out u of xt, this is f of x plus ct plus g of x minus ct. But I have f and g here. So now you see why I switched to alpha here, because if I'd left this with x, it might be a little bit confusing plugging x plus ct into x. Fine. It doesn't really matter. So this is what? This is now 1/2 times phi of x plus ct plus 1 over 2c times the integral from 0 to x plus ct of c of s ds, and again, I don't care about the constants, plus 1/2 phi of x minus ct minus 1 over 2c times the integral from 0 to x minus ct c of s ds. Oh, right. What do I do here? So I can combine these two. So this is 1/2 times phi of x plus ct plus phi of x minus ct. Okay. Well, let's see here. I can swap the order of this integration by changing this minus to a plus and swapping, right? And having it go from x minus ct to 0. So let's do that. So this would be plus 1 over 2c times the integral from 0 to x plus ct c of s ds plus 1 over 2c times the integral from x minus ct to 0 of c of s ds. Oh. So combining these now. This is 1/2 times phi of x plus ct plus phi of x minus ct plus 1 over 2c times the integral from x minus ct to x plus ct times c of s ds. There we go. Just like it's 1746, we have shown that this is exactly the form this solution has to take. So there it is. All right, there's D'Alembert's formula. So D'Alembert's formula is going to be ridiculously influential for all of our analysis for the rest of this chapter. For instance, let's write out a specific example that I'll talk a little bit about next time, but I'm going to write out a specific example and leave it there. So, example, let L be greater than 0. Suppose that phi of x is sine of x over L, and c of x is 0. Think about physically what this means, right? My initial velocity is 0, but my initial displacement is this sine thing. Then check that this is the case. D'Alembert's formula gives a solution to the wave equation. Let's write out D'Alembert's formula. So here's my IVP and its explicit solution. Here's D'Alembert's formula. So let's check that this actually, right, c is 0, so this integral term is 0. So So all I have to worry about is this. So what do I get? I get that u of xt is 1/2 times sine of x plus ct over L plus sine of x minus ct over L, whence my favorite trig identities allow me to rewrite this as sine of x over L times cosine of ct over L. So there's my solution. Now, you might notice something about this solution. I'll talk a little bit more about this on Monday, so in the next lecture. But you might notice something about this solution. So first of all, the thing you might notice is that this solution splits as a function entirely of x and a function entirely of t. Right, so the question is, would we expect that in general? Well, maybe not, right? We'll have to think about that. It turns out this is a pretty special solution, but D'Alembert's formula just immediately gives us this thing. Okay, so we'll think about kind of the implications of this next time. And so I think here's a good stopping point. So that's all for today. Continue on here for the next couple lectures, and we'll finish the 1D wave equation fairly soon, maybe in another lecture and a half or so. Talk about the second, third spatial dimension wave equations, and then we will be touching on a few topics that allow us to discuss the other two of the big three, which are the diffusion equation and Laplace's equation. So we're going to be jumping through, touching on all of these things, and then coming back to all of them, kind of at the end with a different type of tool, a type of tool that's going to allow us to write out special forms of solutions to these things more generally. So anyway, that's the deal. I will see you all next time.